virtual visit. So we will look at physics and biology aspects in our virtual visit of CNAO. Angelica Faccoetti, who you have already met, together with Marco Pulia, will be taking us for this visit. Angelica, I hand over to you.
Hello, thank you. Thank you very much, Nicholas, and good morning, everybody. Marco is here with us, and I think that he is going to start with a live visit through a camera into the synchrotron. So I leave him
Yes.
the floor.
So
Marco, if you are ready.
the screen.
Okay.
Okay. So now this is our synchrotron room. We have this. Oops, sorry, too fast. I have to take. My webcam is too fast for me, but apologize for this. So we can observe the synchrotron room with this webcam. I must have changed some setting. Anyway, here you see the vertical line going on. You can see this blue magnet there, which is the one used to select the treatment room. You see in this magnet we have one vacuum chamber entering and 3 vacuum chambers going out. Depending on the polarity of this magnet, the beam is deflected to the left into treatment room number 1, to the right into treatment room number 3, or when it is off, it goes straight into treatment room number 2, which is the one where we have also the vertical beam line that you see going up and then going against this wall. On the left of this wall, there are the treatment rooms. Now, here you can see, the beam line bringing the beam to the experimental room. After this, on the left here, let's say behind the wall, there is the experimental room. This is a stair to go above the line, because otherwise you would be blocked on the side there. And then behind, you see all these cable trays coming out of the wall. This comes from the power supply room and bring the current to all the magnets of the accelerator. And then, of course, we have the main ring here of our complex. Here you have these 2 boxes in the middle, 1 and 2, which are our 2 ion sources, one for carbon and one for protons. And you see here a new beam line, unluckily without a source for the moment. Here you see the solenoid that is in front of where the source will be, and here there is the space for the new source, which is going to be installed shortly, hopefully. Let's say the source is in a INFN building 1 kilometer away from CNAO, and we are waiting for the authorization to bring it in, and then we can start the commissioning, of course. So we have the 2 sources, the third one virtually here, and then the beams coming from each of the sources is transported in a standard magnetic channel until this part here. You see, we have this pink object here, which is our LINAC. It's just in front of just upstream the LINAC, we have the RFQ. Here you can see a green solenoid as well. And then on the other side of the machine, we have setta, the injection region. You see in orange the magnetic setta. This tank here, which is not so easily seen, but this tank with the dumb physical on it is our injection electrostatic septum. You see with this is the electrostatic septum. You see the high voltage cable coming in. And on the right here, we have another tank like this one, like the one we saw before, which is the extraction electrostatic septum. Then we have on the near side here, oops, this red barrel with HITR written on it, which is our radio frequency cavity, the one that accelerates the particles. And here we have in yellow the resonance driving sextupole. This is a non-dispersive region in our accelerator. Then we have a symmetry along this axis, one period and another period on the left in our accelerator, in our synchrotron. These two sections, 1 and 2, are dispersion free, and here we have two dispersion bumps. On the left, we have this big blue guy, which is our Metatron core, this guy here, which is used to push the beam into the resonance. And on the other side of the machine, somewhere here, it's not easy to see, but we have our RF knockout exciter here, which is being implemented, and it will be used as an alternative to Metatron for extraction in the next future, near future. It's the first step towards multi-energy extraction in our machine, which is not particularly comfortable with the Metatron core extraction. For multi-energy extraction, the RF knockout is much more suitable. And then, well, just to mention it, you may have noticed there are no columns in the synchrotron room, which means that it's also from the building point of view is anyway a non-trivial thing. You see here on the roof we have these beams, which are 37 meters long, 2 meters wide, 2 meters tall, more or less. And they were prefabricated outside and then brought in with the track. You can imagine a track with a 37 meters beam on it. And the track was coming in from this door there with the beam on it, with 10 centimeters on the left, 10 centimeters on the right, more or less on space. So each time that I have to park my car in my garage, and I have the impression that maybe the door is tight, and then I think to the guy with the lorry and these beams when he was entering into the CNAO to install these things, and I say, no, okay. Then I have all the space I need. Well, this is, I don't know if you have already had a lecture or heard how the beams or the CNAO accelerator is made, but we have in blue our dipoles. We have 16 dipoles. We have in green, here light green, our quadrupoles. We have 24 quadrupoles in 3 families. In orange, we have steering magnets, not subdivided in families, otherwise they would not be very useful. And in yellow, we have seen the resonance driving sextupole, but we have 4 other sextupoles in yellow here, which are used to drive resonance, the one that we saw before, and the other 4 are used for chromaticity. What else? Well, basically these are most of the magnets. Then we have a number of weird magnets like the Metatron core that we already mentioned. We have this plastic magnet here, which is an L4 quadrupole for fast correction of the ripple. And then we have, you may see these red cables. These are pulse forming network for the tune kicker, which is here. And well, there's plenty of different types of magnets, like in every accelerator. I would say that we had an overview on the accelerator. If you have questions on the accelerator, we can maybe discuss it. Otherwise, we have a walk around now, and we go and visit the treatment room or the experimental room. So it will be a little bit slower because we are moving physically from one room to the other. But if you are patient, we bring you around now virtually. We have questions or curiosities about the accelerator?
Nicholas.
Yeah. What are those red spools exactly, Marco? Do they have to be so long, or is it because you connect?
These are pulse forming network. Yes, they have to be a given length because let's say the electric signal sent to the fast magnets, to the tune kicker, it has to go to the end of the cable and let's say kind of rebound back in order to make the pulse, let's say a square pulse of the duration that you want. And the tune kicker in our machine has to be, let's say, able to go up, stay up, go down, and be off in less than a machine revolution, like every tune kicker. And at the fastest, let's say 400 MeV carbon ions, they make one revolution of the machine in about 0.3 microseconds. So our tune kicker has to raise in less than 80 microseconds, something like this, to go up and to go down. And so this is not a standard switch. You need these special pulse forming networks, which need cables to, let's say, to be designed. I'm not an expert in fast power supplies, but this is what it is. These two windings of coils are to shape the pulse to the tune kicker, which is here. Are there other questions? Okay.
Matthias. Yeah, we have one, Marco.
Okay.
Yes, regarding the sources and the Linux is inside the ring. If money wouldn't play any role and space would also play no role, would you still put the sources and the Linux inside the ring, or would you put it outside? Because I imagine every time you have an issue with the source or with anything, you have to shut down the entire treatment. And in Marburg, we have it separately. So it's easier, for example, if the carbon source shuts down, we can still treat protons because we can easily access it. So if money doesn't play a role and space doesn't play a role, would you still build it this way?
Well, I presume that if there was no limitation, I would go to have them outside. But let me be a little bit bad against myself and against physicists in general. There is an advantage in having the sources inside. That is, that cannot be accessed. Otherwise, the source guys would spend time there trying to improve, touching things. It would be a temptation. And I'm not sure that it would be better in this respect. Having them inside, we ran smoothly. We didn't have many often very often problems with the sources, and I have the impression that if I had the right or the possibility to access them, then while you're playing with the protons, you want to open the carbon source and change something. I'm not sure that it would be operationally wise. So I don't think that from this point of view, it's a big gain, but of course, having them outside is more comfortable in principle when you need it, which is not often, but why not? If you have no problems on space and money, why not?
Thank you.
Other questions?
Matthias.
Yeah, then another question regarding the Betatron resonance or the knockout extraction. If the knockout extraction is ready, will you use knockout extraction exclusively, or will you still use for the standard treatments use the Betatron?
Hard to say now. I guess that as soon as the RF knockout will be operational, it will become probably the standard extraction system. But still, we will not remove the Betatron from the synchrotron. And as an example, one of the things that I would like to do in future when I will be lucky and so on is to try and accelerate at the same time carbon and helium. Of course, it will be tough. I don't know how much carbon-6 I can get from the new source, but as a test, I will do it. And if you want to extract at the same time carbon and helium, the Betatron core is more indicated, is more suitable than RF knockout, because otherwise they would have two different frequencies. Well, I presume you can do it in both ways, but with the Betatron core, it's more natural, let's say. So I think we will use both, but the standard one will become RF knockout.
And thank you very much.
Any questions? Okay, let's stop sharing then. And I will connect from my phone. Let's see how it works. Oh, okay, very good. Now I rotate this. No, it doesn't rotate. Why not? Okay, now you can see Angelica, and we can move. So, very exciting. Offices on the left and on the right. Treatment planning room. With treatment plans on the screens. Regards from the HITR school. And now an even more exciting staircase. You hear a fantastic noise of when we're closing the synchrotron room. So here we have our control room. Che è successo? Vabbè. Ok, we leave. Not the right moment. Yes. So let's check if we have an accessible room.
Marco, we lost you.
Andiamo in sala. Grazie mille. Can you hear us?
Yes. We
Okay.
lost you for a short while, but you're back.
The Wi-Fi hotspot in moving from one side to the other. Okay, so unluckily or luckily, I don't know, put it as you want, we have problems with the accelerator, so there are no patients in this moment. This is a treatment room. You can see the nozzle here. That's our dose delivery system. It's made by two boxes. Don't know if it's clear, but it's 1 and 2 boxes. Here on top, we have this big cylinder, which contains flat panels and X-ray tubes to make imaging at the isocenter of the patient. When needed, they have to be deployed. Now they are retracted. This is the treatment couch. It moves on an air cushion, and it can, of course, rotate and move. It has 6 degrees of freedom. And what else? This guy here that you see in front of us, this is the inside detector that Giuseppe Bisogni illustrated yesterday. So it's for online PET. You have the two PET heads, above and below, and the particle tracker. What else can we see? Well, we have a C-arm, a robot, let's say, which is being installed. We have a similar system in room number 2. And since our doctors liked it, we are installing it also in room number 1. This is, let's say, an X-ray tube here and a flat panel, and they can be used to make a cone beam CT as well, which is what our doctors like. Not in the treatment position, because in the treatment position, the space is occupied by the big cylinder, I presume. So like in room number 2, you will have to move the couch in a measurement position, imaging position. You take the images and then you move the robot back to the treatment position with the patient on top. And what as well, since there is no problem, we might go to room number 2, so we see also the vertical beam line. C'è un paziente? No. Scusate. No, sorry, we are starting back again, so we can go upstairs now. So that we can visit the radiobiology lab, and then we go to the experimental room. Well, I could show even the position now. This is working progress. Okay. Back on the stairs.
Okay. Here we are. Good morning. And this is our, sorry, it was too much. So this is our lab with my colleagues. We have two cabin floors working and incubators. And sorry if you heard the noise, but this is how it works normally. Then, of course, we have a couple of microscopes. One is an inverted one, to be able to see the flask. So there is enough space to move and see the flask. And then we have another one that is switched off at the moment, is a fluorescent one. And that's, yeah, then we have also small instrumentation. One of the we have. And hopefully in a couple of years, as you can see, we have some work going on outside. So next couple of years, we will have more space and more room to dedicate it.
There are improvements that are possible in this lab. We have a fridge and there is no beer inside, which is definitely a bad idea.
We have also very not temperature refrigerators without ice cream.
They make bad choices of what to put in the fridge. So right. Again, another side of the yard. Okay. Stairs again. I still hope that you abbiamo lasciato la webcam accesa in ufficio da me. Si vedono le bottiglie. Bene. not everything is next to each other right now. I hope you still see me.
Yes, we do, Marco.
Very good. Now into the dark. Almost. And here we go to the experimental room. Chiudi la porta se ne suona. Okay. So
Did we get cut off? Let me see if I can. Oh, I think we got cut off. And I don't seem to be getting through to Angelica.
Okay, we switched from my mobile.
my telephone doesn't collaborate.
Marco, it's yours.
Okay.
Yes.
So this is our experimental room. Not particularly ordered. This is the patch panel for the connections to the control room. These are the lasers. You can turn on the lasers such that we see the various ISO centers. I don't know if you can see properly the green lines
Yes.
on the floor. Okay, these are indicating the position of the various ISO centers. So this is ISO center 2, this is ISO center 3, and this one is ISO center 4, and ISO center 1 is here. In our experimental room, we can bring the beam in different positions according to the experiment that we made. And as you can see now, there is no beam line installed, basically, which is because now it's configured for ISO center 1. So you see the scanning magnets are offline. They are not. This is the beam exit. Okay, the beam comes from here. Behind the wall, there is the synchrotron room. And the scanning magnets are there on the rails away from the beam line in such a way that we can make an experiment in ISO center number 1 here. Otherwise, we can move the scanning magnets on the rails. You have to remove the table, of course, but then you can move the scanning magnets to their position and use ISO center 2. Or you can install 1 or 2 of these tubes and bring the beam to ISO center 3 and 4, depending on the needs in scanning field and so on. This is the dose delivery system. It is also on rails. It's not so easy to see. It's also here. Here, you see that the rails here. It's also installed on these rails in such a way that it can be moved from ISO center to ISO center, remaining aligned, let's say. And what else? Well, the big thing here on the roof is the air diffusion, because we have to change 15 times per hour the air inside this room. And if you have this flow on a small tube, then the velocity of the air is large. It would perturb the experiments. So a large diffuser helps to reduce the airspeed. And what else? That's basically it. I don't know if you have questions.
Do you have any questions, Joe? Doesn't seem like we have any questions so far.
Okay, so we can go back to the office, I would say. This is the small the control room is a little bit messy in this moment. I apologize, but it has a window, which is not common, at least in general, in control rooms.
Okay, it seems like lost the contact again. Let's see that it comes back. Ah. If we are a little bit patient, I think we can wait until it returns.
Okay.
Now we're back.
Huh? Okay.
We were lucky that we didn't have too much noise
No,
today.
yeah, today you and we were lucky.
Do you have construction there?
And just in front of us, there is the hospital of Pavia. So we are definitely in front of it. And on the other side there is the university. So actually we are in the middle. Okay. So the bottles will. Okay. This is that.
I think you can disconnect and we continue from the office. Okay. Are there other questions?
Any questions, guys? I think we can proceed. Ah,
Oh, we have a question in the chat.
Sorry.
So we have a question
Yes.
from Pedro Calvo, who says, regarding the iron source, is there any significant difference in the new source that you're pending to install?
Yes, it's a new type. It will have superconducting magnets instead of permanent magnets. So in principle, it should be more powerful. But the main point is that it can be dedicated to new ions without perturbing the operation of protons and carbon for clinics, let's say. The idea is not to perturb, not to use one of the clinical sources and have a dedicated one. In principle, it should produce more intense beams, but still have to commission it before saying too much. It's still an ECR source, but it should ideally be more powerful, but let's see. It will be more powerful. But the point is that we want to make new ions. That's the real different thing.
Okay, brilliant. Thank you. We also have a question from Matthias. He has his hand up.
So the construction site we saw for a short time, was it a construction site for the new dedicated proton therapy?
Yes, for the proton therapy and for the BNCT.
And the new labs.
And the new labs, exactly. Where we can have beer in the fridge as well. Improve.
Okay, thank you. I don't think there's any more questions so far. So, oh, there's Nicholas. So,
I was wondering, Marco, do you keep many spare elements of the machine? You said that you have so many dipoles, so many quadrupoles. Do you keep some spare just in case, one gives you problems? Or
Absolutely, yes. The point is that you cannot have a spare of everything, and the thing that breaks is the one from which you don't have a spare.
of course.
Not true. In general, spares are useful and you should have them. It's true that it happened to us some years ago that we had a fault in the big 90 degrees dipole, and in this case we didn't have a spare. So it took longer to have them replaced. So if possible, the more spares you have, the better it is.
And when it came to construction, how long did it take, Marco, in fact, to build?
The new building.
Not only the building, the whole infrastructure, in fact. So from the design to first beam, first treatment beam, how long did it take?
The CNAO site, we started digging in 2005, and we had the first patient in 2011.
That's actually quite good. 6
years.
years.
This was a very good performance, I would say.
Yeah.
The new building, they just started digging a couple of months ago. And in principle, they should complete the building at the end of next year. Angelica, correct me if I'm wrong. And the new accelerator, the proton therapy machine, is already built and waiting to be installed, as far as I understand. It's in a store in Japan. While the BNCT, I have no idea of the state of construction, but it should be ready together with the end of the building. So,
and is CNAO planning to increase its staff complement, Marco?
Hopefully so. I guess that we will increase the number of personnel, the number of persons working here, because two new machines will require some more personnel. Especially the proton one will be running in parallel with the present one. So you will have one more treatment room, which will need doctors, technicians, and everything.
Can you remind us what the staff complement of CNAO is at the moment?
Well, I think we are around 140 persons, 120.
Yes. Yeah.
Okay.
Equal gender, female and males, and quite young median age. I think something like 36, something like that.
And also in the high levels, I mean, our scientific director is a woman. Our clinical director is a woman. Our administrative director is a woman. So it's At CNAO, there is no gender gap in all these, in the careers. So
Yeah, we still have the problem with the physicists, but okay, we have to.
you have to live with physicists, which is painful, but
We need, let's say, professional balance.
yes.
Okay, I'm seeing two other questions. Yeah,
Yeah,
Joe,
we have a question from Christa.
Thank you for the tour. I was just wondering regarding the treatment planning system in CNAO, do you use some commercial solution or you've created some treatment planning system of your own, like the algorithms and everything?
We use RayStation research, and you cannot write your own program so easily because to treat a patient, it has to be C-labeled. So it's a non-trivial operation to get it. So it's in general, it's always a commercial solution. I wonder what it will be for the BNCT, because in this case, I don't know if there is a C-labeled treatment planning. This I have no idea. Angelica, do you know if there is a C-labeled treatment planning for
No,
BNCT?
I don't know.
Not to my knowledge, at least.
Manjit has raised hand.
Yeah, sorry, thanks. I had a question. So how many people do you need for running the actual machine?
For running
Besides
the
the clinical
machine,
people, yeah.
the clinical staff or the technical?
No, the actual, the physicists, the engineers and so on for running the actual synchrotron, technically speaking.
So the technical division is 34 people, if I'm right, which includes about 9 operators, and physicists and engineers.
Okay.
We have a largish staff from this point of view, if you want, but at least people are here with the competencies. It's the people that do the maintenance to the machine, and it allows us to be faster in maintaining the machine.
Because the reason I'm asking is there's been a question about the number of staff you need for running a synchrotron-based machine versus a cyclotron-based machine, and roughly, because I know that's quite a major expense, both for you guys, but also I presume MedOstron has more or less the same number of people, right?
I think that MedOstron have more people than we,
But, okay,
but
so
Heidelberg, as an example, they have less.
yeah, well, they've been running for a long time, so you know, and so okay, so it's around 40. Okay, just was curious. Okay, thank
This
you.
is what we have.
Yeah, thank you.
I
And it's
guess
enough.
that if you, yes, I think so. It looks reasonable to me. At least it looks to me that it runs smoothly. You can also make the choice of asking the vendor if you buy a system. You can ask the vendor to operate the machine, which is what happens generally in the commercial centers.
Well, in the other type, but I think with the type of machines we are talking about here, you know, in the Dual Ion, Heidelberg, MedOstron, you guys, I don't know about Marburg, it's very difficult to get a vendor to run that because they are not really sold by vendors, right?
These are in-house built machines.
Yeah.
Which I still
Okay.
prefer personally because I like
Okay.
to build
All right,
machines.
thanks. Thank you. Just wanted to know because, you know, when we
Yes.
talk about costing, it's not just how much a machine itself costs, but how much is the maintenance running costs and, you know, for 10 years, 20 years, etc. So that's why I was curious. Thank you.
Welcome.
And we have another question from Christa.
So regarding your plans of BNCT, or also like sort of already the ideas on like when you would use it, is it like mainly for some complicated cases, or like what's the plan for the BNCT clinically, I guess?
I don't know exactly which kind of patients they plan to treat. Angelica, do you know which kind of tumors they are foreseeing to treat with PNCT?
Well, actually, the aim would be radio-resistant head and neck cancer, and they are also talking about some oligometastatic tumor. And that is, let's say, the starting. And of course, we are also discussing about melanoma, something like that. But actually, in CNAO, there is a strong expertise in head and neck cancer. So probably we will start from that one.
Okay.
They should be more or less superficial tumors, a few centimeters
Yeah.
in depth, not too much. Otherwise,
Yeah.
there.
Okay. Thank you. Thank you.
Right, well, I'm not sure if there's any more questions. I can't see any in the chat or in the Slack. So, yes, thank you very much, Marco and Angelica.
Thank you,
and
guys.
Dr. Nicholas.
Okay, all right, thank you very much. So that was a very interesting virtual talk of virtual tour of CNAO. And we thank you, in fact, for showing us the heart of the machine. Okay, so we can now stop for a short coffee break. We will meet again at 11:15 for our next session.
Okay. Bye-bye.
Bye. Thank you.
Thank you very much. Bye-bye.